Netflix or Amazon are both web-based services, and this is why they are able to collect vast amounts of data with minimal efforts. However, our algorithms themselves did not exploit any aspect of being online. Indeed, even if Netflix suddenly lost internet access and therefore connection with their users, they could still run the user item-based recommendation system and predict missing ratings accurately. What ability do we gain by being online as opposed to offline? Well, we can interact with the users, get the information we need to move on to our next goal. Consider the following silly example. Let's say that Netflix has just bought the rights to add the movie Moneyball to their catalog, but they are not sure what to make of the side information that comes with it. Is it a sports movie? A finance movie? A teen movie? It has Jonah Hill in it. A chick flick? It has Brad Pitt in it. Let's say it's difficult to automatically predict who is going to like this movie. What Netflix could do is to recommend it to key users and adjust recommendations according to their feedback, in real time. This is called active learning. This is in contrast to passive learning, where Netflix would select a large group of users and wait for everyone's feedback before making adjustments. The advantage of active learning over passive learning has been demonstrated empirically and mathematically. Active is always better and is implemented in many aspects of our lives. Perhaps one of the first places where it was used was in clinical trials that are now run in phases. If a drug performs well on the first patients, it will be used more aggressively on subsequent ones, but if it has disastrous effects, the dosage may be adjusted in future phases or the trial may be cancelled altogether. The idea behind active learning is quite simple. Collect information as often as possible, not only to make future decisions, but also to guide future information collection. Web interfaces are a wonderful tool to perform exactly that. Perhaps the most primitive form of active learning is the 20 questions game, where a person chooses a subject, say an actor, and a player must guess in 20 questions who this person is. If you've played this game, you know that you should split the population you have in mind by about half at every question. For example, let's say the first question may be, is this person a man or woman? Or is this person dead or alive? Etc. As you are getting further down the game, you refine your questions. Let's say that you have used your first questions to establish that we are talking about a dead male actor who plays in westerns. You may want to ask whether he was involved in politics. We train at this game from a young age by playing Guess Who, for example. And there are websites that are freakishly good at this game, actually. So how are computers so good at this game? Well, they know how to split the candidates into two halves very accurately. This is called the bisection method. Why is it working so well? Let's say that you are playing this game and start with a population of n candidates. After one good question, you are left with n over 2 plausible candidates. After another good question, you are left with n over 4 plausible candidates, etc. After k questions, you are left with n over 2 to the k plausible candidates. To be sure of your guess, you need to have isolated at most one subject. In other words, you need to ask k questions such that n over 2 to the k is at most 1. Solving for k by taking logarithms, this translates into k larger than log n, where the logarithm is in base 2. For example, if you started with 1 million candidates, you actually need 20 questions to be sure to win. The main difficulty of the game is, of course, to pick questions that split the remaining candidates exactly in half, but computers are good at this. Let us go back to a more serious game, Tinder. There are about 50 million regular users on Tinder, so in principle, your soulmate could be identified in 26 questions. However, the success of Tinder is based on precisely asking a very simple question, yes or no, say hot or not. Note that the question is not, is your soulmate body mass index above or below 20? This would be boring and Tinder would lose customers. Finding your soulmate based on yes-no questions seems like an impossible task. It's like having a 3-year-old play the 20-question game. Is it Nemo? Is it Grandpa? Is it Mittens, etc.? It's the complete opposite of the bisection method. Instead of splitting the population of size n into two parts of size roughly n over 2, it splits it into two parts of size n-1 and 1 respectively. Unless we're very lucky, it's clear that we need n questions rather than log n questions in this case. Yet, Tinder does it and others also do it. kittenwar.com is a website that ranks the cutest kittens by only asking which is nicest out of two photos. The Beer Mapper is another such example. It's an app that's trying to find what kind of beer you like by only asking which beer you prefer out of two choices. For the Beer Mapper algorithm, the goal is to find two beers, say beer A and beer B, such that by knowing if a user prefers beer A to beer B, then one gets a lot of information about the beer preference of that user. Let's say that the goal is to identify the user's favorite beer. Then, in the spirit of the bisection method, the goal is to eliminate half of the candidate beers after each comparison. How can we do this? Well, the Beer Mapper starts from a geometric representation of beers that is based on ratings and descriptions of beers that were written by beer experts on the website ratebeer.com. It looks like this. Beer Mapper picks two beers that split the landscape of beers into two halves. Say, for example, the user prefers the beer on the left, so we know that the user's favorite beer is in this region. Then we pick two more beers from that new region and repeat until we have narrowed our candidate beers to one beer, the user's favorite beer. Using slightly more complicated techniques, we can find a user's ranking of beers rather than a single beer. Here, the goal is to place the user in this landscape and declare the closest beer his favorite beer, the second closest his second favorite, etc. Placing this user can be done using a method similar to the bisection method that we've just described. The bisection method can go a long way when we're searching for a needle in a haystack, a soulmate on Tinder, or beer in an app. In this case, it is good to keep in mind that active learning can be very useful. In particular, it can be used to establish preferences in the context of personalized ranking.